Hello, everyone. I'm really grateful to be here at ADC to present this topic. I'm really happy to be here to be able to present some work that my colleague Jatin and I have worked on, namely how we can inform our modeling system with physics models and how this can help in achieving performance gains in virtual analog modeling. I want to thank Ricardo for mentioning this talk in his presentation. Please check out his talk in the archives. The work shown in his talk is complementary to this presentation and will help give a better idea of the challenges all of us are facing. I also like to thank David for mentioning RT Neural yesterday in his talk. You can watch his talk on differentiable DSP and where the basics of the machine learning in DSP are covered extremely well. I just want to introduce myself a little bit more. I'm currently a PhD candidate at the Singapore University of Technology and Design. When I'm not preoccupied with DSP or machine learning, I'm a musician, and you can see me in my theorbo in this picture. I play in an early music ensemble called Red Dot Baroque. But I started out as a recording engineer working in a studio, and I soon found out that I liked gear, be it software or hardware, more than the things that necessitated my immediate attention. However, like many other people in their early 20s, I didn't have the financial capacity to quell my gear acquisition syndrome. Some of you might know it as gas, right? I had to find another way, and this led me down a path that has brought me here today. I want to preface the presentation with a short introduction to some key points surrounding this topic. As we all know, before the days of digital plugins, there were these genre-defining audio hardware processors. And in that, I mean that these hardware processors have sonic signatures that are immediately recognizable by listeners and audio engineers of a certain genre or period of music. And some of these famous analog hardware have now become collector's items and have risen in price so much that many professionals can no longer justify owning one. I recall a Fairchild compressor selling for $44,000 US, right? I'm sure some of you have seen that. I believe I do not need to urge this crowd into understanding the need for audio conservation as the context for the choice of topic at hand. Someday the last tube will fail and we will not be able to buy them anymore. There was some discussion about longevity of electronic instruments and analog hardware in Astrid's talk yesterday. I think the strategies presented herein would point us in a direction that would begin to come up with solutions for this potential problem. Namely, I think we can aim to firstly preserve the characteristics of these equipment. And in doing so, we get to understand the interactions behind the scenes, within the circuit, inside the component, from component to component, and component in relation to its subcircuit, and then subcircuit to subcircuit, right? And while doing that, we decentralize accessibility so that more professionals are able to make use of the sonic signature. And lastly, begin answering the question, why? Even though this technology is obsolete, do we still have a preference for this equipment? I think I'm not alone when I feel that with every hardware emulation plugin made, we are continuing to strive towards a closer and closer representation of the real-world circuit. However, this poses some problems. The first being, well, cost, right? And not directly in a financial way, but one might expect that with more circuit modeling, and by that I mean squeezing more circuit interactions into the modeling, we inevitably run into more computation being done, which begins the endless cycle of needing faster computers to run these computations, and us discovering that because of these faster processes, we can squeeze more physics into the model, and the cycle repeats on and on and on, right? And instead, I would like to attack the problem differently. How can we better make use of current technology that could be from something as simple as a microprocessor or a single board computer on an embedded device to the average user's processor of today? We should not forget that many professional audio engineers avoid upgrading for a long period of time, albeit for reasons like financial ability or stability of workflow, etc. By doing more with less hardware, we are also allowing users to fight obsolescence and potentially, if I dare say, reduce e-waste. I realize that these are lofty dreams, but I believe it is important to mention these facets surrounding the topic, especially in light of the current state of our planet. The proposal in this presentation is to make use of machine learning to keep computation costs low on the user end by paying it upfront with machine learning, deep learning, AI, whatever we want to call it. In being a trainable universal approximator, the developer can then pay this time cost, which results in reduced time cost for multiple users. And this reduced time cost scales with the number of users. I would also like to add that in this vein, our belief is to work against the current trend of big network sizes, which would depend on hardware getting faster for real-time inference. Rather, we want to allow small networks, and I'll get to how small these networks are later, to succeed at the given task and really squeeze as much performance out of a simple network architecture such as a dense ReLU or a dense 10H network. And this brings us to our first section on physics-informed neural networks. In the paper by Ricey et al., it is defined to be a neural network that are respecting the laws of physics that are provided to the system during training. The method in the paper very roughly boils down to using physics models as a regularizer in the loss function of the network during training. This has shown impeccable results in the domains of scientific computing. How does this help us, right? Well, there's always some nonlinear behavior that separates the real-world circuit from the ideal version of the circuit. In a way, the physics model helps us to strip away as much of the understood linearity and also nonlinearity a bit of it, right? The physics model also provides a way for the person training the model to guide the model towards the optimum parameter space instead of relying on self-discovery through optimization methods. There is also reduced heuristics of toying around with model creation, as we can retain the use of our underlying assumptions or prior knowledge of the circuit and being modeled. And I want to quote, "If I have seen further, it is by standing on the shoulders of giants." Right? Since all this work in modeling the physics has already been done for us, it would be a pity not to make use of it and simply leaving the investigation to our black box companions. In utilizing the physics model, we are also able to feed the model with information about the interactions between components. And conveniently, the model might also handle other parameters that our physics model does not account for, such as manufacturing tolerances, hidden variables that are not part of the ideal physics model, potential interaction between components and states, and other such real-world factors. As I mentioned earlier, the underlying impetus is to keep the models small. And these small models will be more cache-friendly compared to larger models that are directly trained for input-output mapping. We try our best to strip away as much of the known linearity of the system, such that the model only handles the unknown nonlinearity. Some of you might be familiar with lookup tables and are asking the question, why don't we just use lookup tables, right? I have the quote from this presentation in ADC 20 about this. And I really have to thank this presentation, as it was one of the initial inspirations of this endeavor. Unfortunately, we can't run away from dimensionality and the speed at which lookup tables scale. I know so far I have assumed that there is some level of understanding behind how machine learning works, and I will attempt to abstract some of that into a few lines of strategy. In most cases, we have some input data, x sub I, and some output data, y sub I. And we know that this problem can be solved if we can achieve some mapping M. We say there exists some function M that takes in input X and gives us Y, right? rigorously. We hope some trainable model, M star, can achieve this mapping through some optimization. And some people call this training, to quote David, to help support the model, especially in audio-related tasks, majority of the times, not in real-time environments, but we use some feature extraction methods to generate features of the input data x sub I, and it might be easier for the model to achieve the mapping M if it was from a different feature space. And finally, we train and monitor our loss, and at some point, the model can no longer provide a lower loss per unit of time than we have, and we set that as the cutoff point. Right? I want to keep this as inclusive as possible, so I've avoided using LaTeX at all in this presentation. So if you really want to talk about the rigorous mathematics behind all of this, I'd be more than happy to address this later on outside of the presentation. So, yeah. So what if we instead decided on the feature extraction method? What if instead of deciding on the feature extraction method, we let the model train for some latent representation, and we embed the physics model inside of the neural network? We then get a model that is a white box model embedded inside a black box model. These few slides present previous work on the topic. In a work proposing what I call physics approximating neural networks, we create a network in the architecture shown in the image on the right. There is a layer called the approximation layer, which is preceded and proceeded by dense layered neural networks. Of course, these dense layered networks could be of any layer type, but in the paper, it was a dense layer. In case you're wondering, in the paper, the dense layers were about, on top, the pre-processing layer was 2 by 8, and then the bottom one was 5 layers by 8 wide, so still very small. So these dense layers are neural networks that are thought of as pre- and post-processing sections of the network. The network then trains to pre-process the input data to provide a latent representation to the approximation layer, and the post-processing network aims to map this latent representation to the true output. The approximation layer is an operator layer, or operator-based layer, and I cite this paper below, reference number 4, as the reference that looks very similar to this, which they call it neural operators, but it's a bit different from the way I have done it. And it's made of the operator structure of the physics model given to the network. In each non-input variable is replaced with a trainable variable, which in this case I will call theta. So if we look at the arbitrary physics model, we have this del s square x over del h square. We don't have access to this, so we replace that with theta number 1, or theta 1, and then we don't have g, so we replace that, but we do have x, because x is the input, right? And then we don't have c, so we replace that with theta number 3, and then that gives us y hat, right? So this is the approximation layer, and we call that f star. So if we put this back into the model m star, we can see that input x is first presented to m star pre-processing, which is then fed into the trainable f star layer, and then it's fed into post-processing m star, right? So then in this way, your model trains through this operator-based layer, which informs the physics of the model. And if you read the paper on neural operators, they say that we tend to think of neural networks as sort of set mappers rather than function mappers a lot of the times. So they tend to do that more. So in this case, we try to help the neural network become a function mapper by sort of giving it these operators to work with. This has proven to be a useful method in modeling individual component nonlinearities. The graph here shows the error of 3 different models predicting the output of a film capacitor. The underlying assumption here was that film capacitors inherently add some nonlinearity to the circuit. In green, we see the pan model provides a lower error compared to the equally sized dense layered model. So the pan model is 2 by 8 plus the approximation layer, then 5 by 8. So the dense layered neural network was 8 by 8 network. So the same size. And we see that it gets lower error. And then we also get a much lower error compared to the model that assumes no nonlinearities. We could also do things the other way around by embedding a black box model into a white box model to achieve some performance gains by sidestepping some of the computations that contribute to most of the time cost. I would like to speak more generally about this topic, as the details of each of the methods would take away from how the method can be easily implemented. To give some idea of the ways this might happen, we can see two diagrams on the right. One of the diagrams shows a series of functions which strip away some linearities, and these might be parameter controls from the user, or such as knobs or whatever. And the solver handles the last ugly bit that we don't have a good way to solve in real time. The other diagram shows some linear functions contributing to an output that feeds into a solver or a nonlinear function that we need to compute in order to get the output. In both cases, we usually see a solver or a nonlinear function that might cause either a sacrifice of accuracy or additional time cost. I'll give a full rundown on this later, but in reference number 5, the problem of having to evaluate the Lambert W function at least once per sample was alleviated by replacing the diode equations in the WDF model with a small neural network. With the WDF model still handling other parts of the circuit. This method has been further extended by Dirk and Champ in reference number 6, below was used on vacuum tubes. I want to speak a little bit on wave digital filters, but only in broad strokes, partly as a review in case you were not able to make it to Ricardo's excellent talk yesterday, but also as this topic runs quite deep, the specifics might differ for each varying project. So I present again everybody's favorite diode clipper. Once again, we see that below shows a typical WDF graph. We use this series and parallel adapters to construct the circuit. This also serves as a representation for how information will flow in and out of the graph. I point to great resources on this paradigm, namely Fettweiss's and Kurt Werner's body of work. Just a little bit on the data flow. At each time step, we see arrows on top colored in red showing information flowing up towards the diodes. And then below, we see the arrows colored in green, and that shows the data flowing away from the diodes. We're then able to replace the diodes with a small neural network, and in this case, this allows the WDF model to continue handling the elements that we assume to be linear, such as the resistor and the capacitor. The WDF model also continues to handle the state of the components, such as capacitors. In doing the embedding, we also allow for the training to make use of the entire WDF graph structure, where the data flows in and out of the graph. In other words, the neural network graph is extended with a feature analysis method, which is the WDF, and this feature analysis method is then appended to the neural network graph as a WDF model. So the data flows into the WDF graph, which then trains the neural network on top, and as you propagate the data out, you calculate the loss function at the end of it. So then you can actually train the whole graph at one time. And I'll talk more about this at the end of the talk. Some of the added points I want to speak about. That in this case, we are focusing on speed as well as accuracy, and the first instinct was to utilize dense layered neural networks. Contrary to this, if you did not have a WDF model to handle the state of the system, you would use the dense layered neural network to model the entire system. Handling state would not be as trivial as just allowing the model to train for it. Next, without too much emphasis on the speed of dense layers compared to others, if we were to introduce other more complicated layer types, other limitations would arise, such as sample rate dependence, and this would go against the flexibility and modularity of the WDF paradigm. Lastly, however, it is still important to make use of prior knowledge, intuitions, or hunches about the system. If you feel that there is a component that has some time-based nonlinearity that was previously not accounted for, please feel free to use GRU or LSTM or something like that. This brings me to the final part of this presentation, which is how easily we can make something like this happen. I would like to introduce to you the methodology that we would like to put forth. First of all, the Differentiable Wave Digital Filters library is available on GitHub. I'll be posting the slides there as well. Feel free to scan the QR code to peruse in your free time. The library was developed in Python, allowing interfacing with machine learning and AI libraries such as TensorFlow. I want to give an overview of the ideas behind the motivations of this DWDF library. And that is to firstly construct the WDF model of any circuit you would like to model, and then just simply choose which part of the circuit you want to replace with neural networks. The first step is to build the actual circuit in the real world. I want to quote my supervisor in telling me that the universe is the best computer and is able to do everything in real time, no matter how non-linear. Wise words. I recommend ordering a PCB for the data collection as it mitigates issues faced when using a breadboard. Also, trace impedances and component distances for heat or magnetic interference modeling can be tweaked or kept constant depending on what you want. You can also see that other precautions were taken, such as the metal case connected to earth ground covering the circuit during data collection. In this presentation, the circuit was sampled with the IDMT SMT guitar dataset from Fraunhofer. This was done in 5 discrete potentiometer settings between 10K and 100K ohms. And also variations of the circuit were constructed. The table here shows all the variations in the nomenclature used in this presentation. So 1U, 2D would be anti-parallel diodes arranged in the configuration shown here, right? So 1U and 1 up and 2 down. More diodes in this case would introduce variations in the parameters that the Shockley model doesn't account for. Next, we construct a white box model of this circuit. So the WDF model of the circuit was made using the DWDF library. This also allows us to benchmark against the known WDF method. Although we could train the model directly from the DWDF, it would be slower, due to overheads introduced by WDF elements and as well as Python. So we pre-trained the neural network separately on a SPICE model derived from the Shockley diode law. You can see the data used to train the model. The model was trained for 2,000 epochs with the Adam optimizer, and these figures on the right are from the 2x8 model's pre-training. We used a combination of mean square error and error to signal ratio as our loss function. This model's trained parameters were then used as the initialization weights and biases for the DWDF network's training of the real circuit. As alluded to earlier, we want to keep network sizes small, really small. This reduces our search area to a much smaller set of network architecture parameters. You might notice that the model layers width is in multiples of 4. This is because of the SIMD utilization. We then perform the search across these 5 network sizes to see which of the losses are the lowest. In case you would like to know a rough idea of the performance of the network, my co-author Jatin provided a graph of the real-time performance of dense 10H networks as a color graph on the right. This area in the lower left segment, this one, represents network sizes that are around 100 times faster than the duration of the audio being processed. In addition to neural network size search, one might also consider network hyperparameter tuning to set the small model up for success. We tested 27 different hyperparameter settings of the Adam optimizer in 100 epochs, and we then chose those parameters as our hyperparameters. Lastly, I show you the code not as a means of teaching the implementation, but to show how easy it is to set up the WDF model and the neural network in an audio plugin. This has been made really easy by Jatin's real-time neural network inferencing library called RT-Neural. As you can see, once the WDF model is set up, it is just a matter of plugging in the network parameters from your DWDF training session and loading the weights in. In summary, although not like a just add water method, what we are doing can be boiled down to constructing the circuit and recording data in the real world. Then we construct the WDF model with the DWDF library. We perform pre-training necessary to bring the model closer to the desired parameter space. We conduct a network architecture search to determine the best network size. We can conduct some hyperparameter search to achieve the lowest loss possible for the chosen network. And then we implement the plugin with RT-Neural. Next are just some results of the plugin. So if we look at just the 2x16 network, that is 2 layers by 16 wide, these errors are of the test dataset, which is different from the data that was used to train the models. The pre-training error shows the error in pre-training, and that represents the network's deviation from the Shockley model. So in pre-training, you can see the E-4 is very close to the Shockley model, right? And then at epoch 0, now the model represents the Shockley model's error with respect to the real-world data. You can see that the Shockley model doesn't really do a good job at predicting the real-world diode data. And finally, at epoch 500, we see that our network does a better job than the Shockley model at predicting the output. See, the order of magnitude down, right? The time domain plot here shows the testing of the model on a test dataset. You can see on the left, the model at epoch 0, that is to say the Shockley models predicting the real-world signals. And on the right, we see that the model post-training doing a much better job. However, there are still some deviations. Possibility for this, I think, don't quote me, is that hidden parameters are out of the dimensionality of the 2x16 network. So maybe we need a slightly bigger network. Maybe we need to account for some state or memoryless or memory-full behavior or something like that. Here we see the transconductance plot of the Shockley model in blue versus the trained transconductance plot. This shows how much deviation in terms of voltage per current the real-world diodes are in comparison to the Shockley model's representation. This slide shows the benchmarking of the speed of the various model sizes. And we can see that our chosen model is 1.2 times faster than the ideal model, representing the one with the Lambert W function at each step. I'll provide a few seconds to glance through the results. In closing, I want to say that although the circuit shown in this presentation is a relatively simple circuit, it serves as a proof of concept for other more complex circuits, such as tube screamers, tube models, transformers, etc. Not the hugging face kind, like the copper and iron kind. Yeah? In reference number 6, this method was performed on a Fender amplifier. Next, I personally feel that it would be possible to set up some other autonomous methods of network and hyperparameter search, such as Optuna or genetic algorithms like NEAT, HyperNEAT, Lemonade, or even classical optimization algorithms like flower pollination, particle swarm, sine, cosine could even be considered. I spoke a bit about having black boxes inside of white boxes in this presentation. And I alluded to a method of embedding a white box inside a black box model earlier as well. I had come across this proposed term called zebra or zebra boxing, which sounds really interesting. And what you do is you have a white box, and inside that you have one black box or like a few black boxes. And inside that black box, you have a white box informing that. Inside that white box, you have another black box inside. So you can keep going forever and ever. And I'm fascinated by this idea. And I would love to see if there are any available mathematical paradigms to make this happen. Lastly, although not mentioned in this presentation, the DWDF library can also be used for parameter discovery for circuit components. This is covered more in the paper, so I would love for you to check it out if you're interested. In possibility also lies in the future to have a neural method or a meta method to generate the WDF topology for a known circuit. So if we didn't have the schematic of the circuit, it would be nice if we could plug it into this method and we generate the WDF model. So it's probably not a gradient-based approach because I don't know how you differentiate a netlist, but maybe someone can figure that out. And as an additional note, I want to point to my work, NN lactose, as there was mention of differentiating conditional statements yesterday. The lactose algorithm allows differentiating conditions if they are branchless. So please check that out or get in touch with me if you're interested. I would like to thank RT Neuro. Please check it out on GitHub. And thank you so much for your time. I really appreciate everyone that is here for my presentation. I hope you enjoyed this presentation. I leave my contact information here and I'm open to further collaboration. Thank you.